So welcome student, welcome to the students lecture and good morning. So let me start today's lecture. So this is MA415 Algebra, okay, and this is the lecture number 12. Lecture number 12. Okay. Now recall we already proved Syllow's 2 theorem. First theorem and second theorem. First theorem tells you that if G is or some p power r into m, then for every prime power you have a subgroup of that power, right? In particular, you have a subgroup of highest prime power, which are called p-Sylow subgroup, right? And in second theorem, we proved um, we proved that given any p subgroup of G, that will be sitting inside some p-Sylow subgroups, and in particular, any two p-Sylow subgroups are conjugate, right? Yeah. So now today we will count how many such p-Sylow subgroups are there. Okay. So this is called Syllow's third theorem. So that counts the number of p-Sylow subgroups. Okay. So what is the statement? The statement saying that the number of p-Sylow subgroups. Okay. p-Sylow subgroups of G is of the form, the number is what? It is of the form Kp plus 1. That is this number. You remember the number we defined by NP. NP is congruent to 1 mod P. Okay. That p-Sylow subgroups are of this form. Okay, and you also know that you have at least one such things. Okay, and let us give a proof for this, and you can also prove further that this index is actually yeah. So you can okay. So let us just give this proof, and then you can also actually prove further. But I think this is okay. So yeah. So this NP also divides this number, the group G. Okay, so we'll come later. Okay, so how to prove this kind of statement? So proof. So remember what is given. The given is this is some p power r times m and p m or o prime, and here p belongs to p-Sylow. Okay, so what was my symbol? p-Sylow of G, right? Okay, p-Sylow subgroup of G. Okay, then let me just clean this part properly. Okay, so that is order of this is equal to p power r. Okay, so now we consider the set say y. So this is that all conjugates P, the p-Sylow subgroup P. Okay, and now see that this P is acting on Y via conjugation. So what is that map? So the map is that P cross Y to Y by what do you give? So if take any element from P, say H, and then any element conjugates of Y, say Q, and send this to H, Q, H inverse. Okay, and you see that Q is also p-Sylow subgroups. So this is also a side of p subgroup, right? So this is my set Y. Okay, which are conjugates of p-Sylow subgroups. We already proved that any two p-Sylow subgroup are conjugate to each other. So this set is actually nothing but Sylow p subgroup of G. Okay. Yeah. So now this is so now note that the element P is always belongs to these fixed points of P, right? As H P H inverse equal to P for all H belongs to P, right? So that the fixed point set is not empty, right? You already have one element. You know, already have one element. Okay, and so what does that mean? So that means okay. So this is also conjugation axioms. Okay. Uh, this is okay. So this part is okay. Yeah. So yeah. This p invariant element of Y in that set P is already there, right? Now my claim is that this is only one. So claim that set is actually containing only one element P. Okay. So again I will try to find out some counter example. So how to prove this kind of statement? So if not, let Q belongs to that uh, another element. Yeah. Okay. That is an element of that fixed points of P under the conjugation axis. Okay. And then what happened? Then that is uh, H Q H inverse equal to Q for all H belongs to P, right? This is under the actions of pre. It is true, right? So this is what this is your uh, H dot Q, which is nothing but this, right? And this implies what? This implies your P is actually sitting inside normalizer of Q in G, right? Because every element of P normalizes Q. So Q is sitting inside this. Okay. And again, so this implies, you remember in last class we proved that a similar kind of thing. So same thing is true here. So this implies that P is subset of Q. Okay, I think I should give a proof, or I understood the proof, because I have already given a proof of this fact, similar fact in Syllow's second theorem, right? So if P is inside any P group inside this normalizer of Q in G, and then this has to be equal inside Q itself, right? Yeah, and or maybe let me give a proof. Okay, then this. If you forget, then let me give you another proof. Okay, so uh, proof. This is a proof of fact that Q is sitting inside this. Okay, so if not, then can what happen? If not, and then uh, there exists X belongs to P, which is not inside Q, right? And these cosets of Q is not equal to Q. Clear? But you know that in Q, this normalizer, inside normalizer, Q is a normal subgroup, right? So you can have a cosine group, and this order is co-prime to P, similar to your last lecture. It's co-prime to P because the highest power of P is inside Q, so you are cosenting out by the highest power of P, so whatever the left is co-prime to P. Okay, and thus this order of xq something that will be something, say k, which will be with this series of k and p is 1. Again, so what does that mean? That means, so this implies x power k is inside q. Again, you know that x is an element of p, so order of x will be some prime power, some p power p, right? And this k and p power p are co-prime, right? So we have some k1 and k2 belongs to integer such that k1 k plus k2 into p power b equal to 1, so that x can be written as x power k1 k plus k2 into p power b, but then that is nothing but x power k power k1 and x power p power b power k2 by x power p power b equal to 1 identity, right? So it's nothing but x power k power k1. But again, x power k is the element of q, so this is the element of q, which is a contradiction, right? Because we choose, so this is a contradiction. This is a contradiction, right? So what does that mean? That means that P is sitting inside Q. So thus P is sitting inside Q, and so what does that mean? So P is a p-Sylow subgroup, and also this order of P and order of Q are same, right? So therefore, what do you conclude? Your P and Q are same. So what does that mean? If you choose any element inside fix P invariant element of Y, there has to be Q. So thus this fixed points of P is nothing but P, right? Exactly P. Now we will use this orbit stabilizer formula. So now this orbit stabilizer formula implies what it implies. It implies that this p-Sylow subgroups this order of this equal to this fixed points of P, and then blah 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 something, right? So you know already. So this is P and then centralizer. Okay. whatever you write down, that doesn't matter. Some age says that centralizer of age not equal to full p, right? That star. And what is this? So this is the p-Sylow subgroup. This is np. Left hand side is np, right? And you see the right hand side. This ch is not equal to p. So what does that mean? That means this factor is divisible by p, right? So this factor is divisible by p, and thus the sum is also divisible by p, right? The sum. Is also divisible by p. Okay, and hence np will be what is congruent to, and yeah, so and what is this? This fixed point is 1. There is only one point which is fixed points, which is nothing but p. So if you just go modulo p, then it will be 1 mod p. Okay, yeah, so this tells us that okay, so yeah, so this tells us that the np is congruent to 1 mod p. But one more thing, you see that under these actions of p, so okay, so maybe I can yeah, so maybe I will take another actions, and then I will tell something more. Okay, so you see again, so this is actually that proves what I claim, but I want to tell something more. So again, now remark, you see that G is also acting on this set. Why it is what p-Sylow subgroup of G, right? By what? By conjugation, by um, uh, conjugation. This is simple, right? Why? Because you have G cross Y to Y, and then you send then G dot any Q to G Q G inverse. Okay, clear. So conjugation actions, and you also know that this conjugate, any two pieces will conjugate to each other. So you check that this actions is, so this action is transitive. What does that mean? So that means given any two p1 p2 belongs to p-Sylow group of G, there exists some G belongs to G such that p1 will be the conjugate of p2, right? That is the meaning of transitive actions. Okay, now if you have a transitive action, then what happens? Then you have only one orbit. Remember, transitive action means all the elements are containing in one orbit, right? So thus there is only one orbit, right? Because the other elements, so given any two elements, they are actually linked by conjugation. Okay, so you have only one orbit. Now once you have only one orbit, then what happened? Then what do you know? So you know that so only one orbit. Okay, so then you know. Okay, so Yeah. So what does that mean? That means if you collect, then what is NP? So NP is number of p-Sylow subgroups. Then you can also tell something else. So you can tell that. So maybe I can give you one more proof that will be. Um, that will give you more details idea. Okay, so now so how many, so question is the how many conjugates are there. So I can okay, so the question is the how many such conjugates are there, right? So NP, this part is okay. So only one orbit, you will get it. So you can write down your G, this CLO P, these numbers of G, that's the same orbit, only one orbit, right? So now, so this cardinality is NP, and you also want to know that how many so in terms of G, can I say how many such um, how many such what is NP in terms of G? Can I say any kind of thing? So I can write down that this number actually NP is actually it's nothing but index of okay, so let me write down by these. So this is nothing but index of this normalizer of this inside G. Okay, so yeah, so how do you check this kind of step? Here is this. Now you see that what is normalizer of, okay, normalizer capital P, normalizer capital P in G. So this normalizer of capital P in G is what? This is all the G belongs to G, um, such that um, all the G belongs to G such that um, yeah, so G P G inverse equal to P, right? So this is the um, normalizer of P in G, right? So if you have so question is the how many such left cossets of NP in there inside G, right? So if you have a number of left cossets of NP, that normalizer of P in G will be there. See, I don't know P is normal subgroup or not, right? But I know that P is normal subgroup inside NP of G. This is not to me, right? So you can ask this. Okay, so is this, yeah, so 1 minute, so I am missing something. Okay, let me just write it down here. So that is only one orbit. So what does that mean? So that means I should say that NP Okay, so which part I'm missing here? So normalizer of P in G. What I want to tell extra for. Okay, so NP of P is normalizer of power of G, and your number of such conjugates of this P is the index of this normalizer of S. That part we know, and number of such conjugates are actually NP. Okay, so yeah, so yeah, so this is the okay. So this is already you know actually this theorem already proved. Okay, so we call that um, centralizer. Okay, so I think we prove it for a element, right? So we prove that this orbit for recall that we prove that uh, this the orbit number of elements inside the orbit of anything. So we choose orbit of x, and that element is nothing but or index of the stabilizer, right? Now for the case set also you can define. See here what happened here, this axons is on okay, so here the axons in on set, right? So here G is acting on uh, G is acting on the set Syllow's p subgroups. Okay, so now you try to find out what is this. So this axons, what is your G of, see uh, this is collection of p-Sylow subgroups, right? So so if you want to find out what is for example GQ, what is GQ? GQ is the stabilizer of Q, right? So stabilizer of Q is what? A stabilizer of P, say you start with the P. What is stabilizer of P? So this is collection of all G belongs to G such that G dot P equal to P, right? But what is the dot what? So dot is nothing but G belongs to G such that G P G inverse equal to P, right? But this is what? This is nothing but the normalizer of P inside G, right? So what does that mean? That means you find out that this uh, that the orbit of P, the number of element orbit of P is actually nothing but index of this normalizer of these inside G, right? But this is what? This is nothing but this Sylow. There is only one orbit, right? So this is Sylow p subgroups, and this thing what? This is order of G by order of the uh, this, right? But we know this is NP. This is known. So then NP equal to nothing but order of G divided by order of this small subgroup of P. So what does that mean? That means NP is the index of normalizer of P inside G, right? So thus what I want to conclude, NP also divides the order of the group G. This is one of another observation I should say, right? Yeah, so I think this part is now okay. Yes. So what is this final point? So NP is congruent to 1 mod P, and NP is actually divides the order of the group G. Okay. Um, so this is p power r times m, so np divides actually m, because nt in as np is of the np is congruent to 1 mod p, so np cannot divide p, right? So np divides n. So these two are very important observation that will help us to find many examples. Okay. Yeah. Sylow theorem tells us the number of p-Sylow subgroups are actually congruent to 1 mod p, and it also divides the order of the group, in particular that the coprime part of the order of the group, right? Okay, now let us, so what are the corollary? So immediate corollary. Corollary. So immediate corollary, you can say that the following are equivalent. So what are the equivalent? So P is a characteristic subgroup. G start with any subgroup. G is known to you. So P is characteristics in G, and then is equivalent to okay. Or rather, I can say okay. So maybe I can say something more for bodies. So P is the unique p-Sylow subgroup. p-Sylow subgroup of G, that is np equal to 1, and this is equivalent to the following are equivalent. They are equivalent. This is equivalent to say that P is normal, and also equivalent to say that P is characteristics subgroup of G. And there are many more actually, but yeah, I think there is one more. Let me just write down that also. If you have a set, say X is any subset of X, G, so the X may not be subgroups, and such that what happens for all small x belongs to X, the order of small x is a power of P. Okay, so you have a subset whose elements are power of P. Then what happens? Then the subgroup generated by then the subgroup H generated by that set X is a P subgroup. Is also equivalent to this above statement, and the proof are also simple here. Yeah, so first of all, 1 implies 2 is just obvious. So what was 1? So P is the unique p-Sylow subgroup, right? So what does that mean? Unique p-Sylow subgroup means there is only one conjugate. So np equal to 1 implies G inverse equal to P for all G belongs to G, right? There is only one conjugate. This implies this is actually both sides implied by P is a normal subgroup of G, right? And P is a normal subgroup of G, then G inverse equal to P for all G belongs to G, and that means np equal to 1. So 1 implies 2, 2 implies 1 is obvious, right? Now let's see whether I can prove 2 implies 3 or not. Now how to prove 2 implies 3? Now you see, see 2 implies 3 is, so you start with, so let P is normal subgroup of G, it is given, okay, uh, but then we know that then as 2 implies 1, so P is the unique subgroup of unique subgroup of that order that P power R, right? Unique subgroup, and thus you already showed that P is characterized subgroup of G. That whenever you have a unique subgroup of, I remember that was probably one homework, but the proof is simple. Uh, thus P is characterized subgroup of G. So the proof is simple because whenever you, so what does that meaning of characterized subgroup? So it is invariant under every automorphism of P, G, right? Now, if there is only unique subgroup of that order, then every automorphism will give you the same thing. So it's invariant. So it's obvious, right? So 2 plus 3 is obvious because 2 plus 1 you know that, and 3 plus 2 also obvious, and also 3 implies 2 is trivial, right? That we know every characteristic subgroup, every characteristics subgroup is normal. Okay, so yes, so this is obvious. So now question is that whether can we say 3 implies 4, 4 implies 3, or 1 implies whatever, 1 implies 4, 4 implies 1, then also we are done. Now let me just prove 1 implies 2. Now for 1 implies 4, what I can do, so what does that mean? That means P is a unique subgroup. There is only one p-Sylow subgroup, so in P equal to 1. So this is given that in P equal to 1, and then I need to prove that if H is a any subgroup, okay. So now let you have a set X, subset of X, subset of G such that for all X belongs to X, order of X is some prime power, right? So some prime power is some some power of P, right? So now you see that your X is actually belongs to some subgroup, right? P subgroup, and that is belongs to some p-Sylow subgroup. So X will be something P inside something, right? Some p-Sylow subgroup. But n p equal to 1 means what? That means X is always belongs to p-Sylow subgroup. Okay, whenever you have a X whose power is prime power, that X has to be element of the p-Sylow subgroup P, because p-Sylow subgroup is unique here, right? And then so this is true for every X belongs to X. So what does that mean? That means X is a subset of P, and hence H, which is subgroup generated by X, is also a subgroup of P, right? So what does that mean? So H is a subgroup of a P group. So H is a P group. So H is a P subgroup. P subgroup. Okay. Now conversely also you can Conversely, conversely, what you can see is conversely you can tells that, okay, so suppose 4 conversely let 4 is true. Okay, so what does that mean? That means whenever you have a set X such that every element of that set is of prime power, then X has to be a p-subgroup. Okay, that is true. And let you start with your X is the union of um, P, and this P is p-Sylow subgroups. So you choose all the p-Sylow subgroups and take the union. Okay, so you take the union of all p-Sylow subgroups. Okay, now you see that every element of X element, so then for all X belongs to X, uh, order of X is some prime power, right? Prime power A for some element. Because X is element of p-Sylow subgroups, p-Sylow subgroups of order P, so every element of X is prime power X. Okay, and I assume that 4 is true. So what does that mean? That means that X, so this is H, is a P subgroup of G, right? That is given in 4. But the magic is that H is a P subgroup and P is a P subgroup of G of maximum order. So H is a H is a P subgroup and P is a p-Sylow subgroup with what? With P sitting inside H, right? H is the union of those things. So this implies P has to be equal to H. There is no other options. Okay. So which is nothing but the subgroup united by X. Right? So what does that mean? That means uh, that P must be unique. So yeah, so any such p-Sylow subgroups has to be equal to this. So thus there is only one p-Sylow subgroup. This is the subgroup of G, right? Clear? So whatever p-Sylow subgroup you choose, that has to be equal to H, and hence it is unique. Okay, so let's stop today's lecture. So these theorems are lots of involvement is there. So I believe you need to spend more time on understanding this kind of theorem and do write your state comment everything or question to the comment sections. I will try to answer you as soon as possible. Okay, and probably in next class we will learn lots of applications of Syllow's theorems. Okay, and that is one of the main goal, how to apply Syllow's theorem to solve many problems. Okay, so let me stop here for today's class.